Hello everyone, welcome to Brain Blitz Audios. In this episode of NEET Preparation, we'll be dealing with previous year questions of chemistry in medical entrance examinations in India. The chapter that we'll be dealing with is Structure of Atom. This is the second chapter in the grade 11 syllabus for CBSE. Let's begin with the first question, shall we? So this is the first question. The configuration 1s2, 2s2, 2p5, 3s1 shows excited state of oxygen ion, excited state of neon atom, excited state of fluorine atom, and the ground state of fluorine atom. So let's learn something more about the configuration 1s2, 2s2, 2p5, 3s1. So this contains the valence electrons. This is a representation of the valence electrons present in the atom or ion. And this uses quantum numbers which describe the position of each electron in the shell and in the atom. And this is due to the quantum theory of atoms. So in this configuration, the exponent gives you the number of electrons in the particular shell. So the 1s orbital contains 2 electrons. The 2s2 orbital contains 2 electrons. 2p5 contains 5 electrons, and the 3s orbital contains 1 electron. So to find the total number of valence electrons, you just need to add these quantities. So 2 plus 2 plus 5 plus 1. That is equal to 10. Now, when we look at our knowledge of the elements, we know that the atomic number is equal to the number of valence electrons. And so here we have valence electrons 10, and the atomic number for 10, the atomic number 10 is associated with the element neon. And neon's normal configuration is 1s2, 2s2, 2p6. So as you can see, one electron from 2p got excited and it went to the next orbital, that is 3s1. So therefore, the right answer is option B, excited state of neon atom. For fluorine, the configuration is 1s2, 2s2, 2p5 in ground state. And so therefore, it's not equal. And when fluorine, if it gets excited, then it will be 1s2, 2s2, 2p4, 3s1. So option C is also incorrect. And this configuration does not apply to O2 minus. So option A is incorrect. The right answer is option B, excited state of neon atom. Next question. The total number of orbitals in a shell with principal quantum number n is n squared, n plus 1, 2n, or 2n squared. So we need to look at the number of orbitals in a shell with principal quantum number n. So before we go with the case where n is present, let's start with principal quantum number 1. So principal quantum number 1 means we have the first shell. And the first shell has 1s orbital. And this 1s subshell has 1 orbital where 2 electrons can stick like this. What about the second shell? The second shell contains, when quantum number is 2, the second shell has the suborbits 2s and 2p. 2s has 1 orbital and 2p has 3 orbitals. Because s has 1, p has 3, d has 5, and f has 7. That is the number of orbitals present in each of the subshells. So over here, when n is equal to 1, we find the total number of orbitals is 1. And when n is equal to 2, the total number of orbitals is 4. Let's take one more case where n is equal to 3. So that means it's the third shell. The third shell contains 3s, 3p, and 3d. So 3s has 1 orbital, 3p has 3 orbitals, and 3d has 5 orbitals. So 5 plus 3 plus 1, and that is equal to 9. Now the quantities 1, 4, and 9 on the right side can be written as 1 square, 2 square, and 3 square. So since the principal quantum number is 1, and its square gives us the total number of orbitals, which is 1. Similarly, 2 squared gives you the total number of orbitals as 4, and 3 square gives you the total number of orbitals as 9. And this we calculated for each shell. So therefore, the right answer is option A, n squared. The total number of orbitals in a shell with principal quantum number n is n squared. Next question. Positron is an electron with positive charge, a nucleus with 1 neutron and 1 proton, a nucleus with 2 protons, a helium nucleus. So when we are studying about the structure of atom, we mostly associate the elementary particles as protons, electrons, or neutrons. However, there are other elementary particles as well, such as positrons, and then we have neutrinos, antineutrinos, etc. So there are many other elementary particles, and one of them is positron. So having said that, let's look at each of our options. A helium nucleus is option D. Helium has a nucleus of 2 protons because the atomic number of helium is 2. The atomic number is represented as Z. So therefore, option D is incorrect. What about option C? A nucleus with 2 protons. A nucleus with 2 protons would have its atomic number as 2. So a nucleus with 2 protons is basically a helium nucleus. So option C is incorrect. Option B, a nucleus with 1 neutron and 1 proton. This condition is found in deuterium, which is an isotope of hydrogen. And what is an isotope? An isotope is the same element which has the same atomic number but a different mass number. And over here, hydrogen's atomic number is 1 because it has 1 proton, and deuterium also has 1 proton. So the same atomic number is 1. However, the mass number is different because hydrogen does not have a neutron, but deuterium, the isotope of hydrogen, has a neutron. So the mass number is different. But that does not mean that this is a positron. One nucleus with 1 neutron and 1 proton would refer to deuterium and not a positron. So option B is incorrect. The right answer is option A, electron with positive charge. An electron is a particle inside an atom, a subatomic particle with negative charge. And its mass is 9.01 into 10 raised to minus 31. A positron is basically a subatomic particle with the same mass as an electron, but with positive charge. So a positron is basically an electron with a positive charge because it has the same mass of the electron. So option A is the right answer. Next question. The wavelength of visible light is 2000 angstrom to 3700 angstrom, 7800 angstrom to 8900 angstrom, 3800 angstrom to 7600 angstrom, D, none of these. So what is angstrom? This basically is 10 raised to minus 10 meters. So it's a unit of length. And wavelength is the length of the wave, a single wave. Now, when we studied about visible light, we're made to remember that the wavelength of the visible light is 400 nanometers to 700 nanometers. So these are approximate values. They can differ a little bit. But over here, the units are different. So let's convert nanometers into angstroms. And 1 nanometer is 10 raised to minus 9 meters. And so we can write it as 10 into 10 raised to minus 10 angstroms. Because 10 raised to 1 minus 10 would give you minus 9, which is 1 nanometer. So we can write 400 nanometers as 4,000 angstroms and 700 nanometers as 7,000 angstroms. And so which of these is the range that's closer to 4,000 and 7,000? Option C. Because this is almost similar to 4,000 to 7,000. We've mentioned that the value of 4,000 and 7,000 can vary from a little bit from person to person. So the wavelength of visible light is 3,800 to 7,600 angstroms. Let's look at why others are different. 2,000 angstroms to 3,700 angstroms would be 200 nanometers to 3,700 nanometers, 370 nanometers. This is lower than violet, the wavelength. So this is UV rays. This is the wavelength for UV rays, so that's incorrect. And 7,800 to 8,900 is greater than 7,000 angstrom. So basically, this is the wavelength for infrared. So option B is incorrect. And since option C is correct, we can safely say that option D is incorrect. So the right answer is option C, 3,800 angstroms to 7,600 angstrom. Next question. If E is 1.60206 into 10 raised to minus 19 coulombs, and E by M is 1.75875 into 10 raised to minus 10 raised to 11 coulombs per kg, then the mass of the electron is. So E refers to the charge on the electron, and E by M is the charge to mass ratio of the electron. And this quantity, the charge to mass ratio, was used by J.J. Thomson in order to discover the electron. So now in our question, we need to find the mass of the electron. So E divided by M is given as 1.75875 into 10 raised to 11 coulombs per kg. But if you notice, we are also given the charge of the electrons as 1.60206 into 10 raised to minus 19. And since this quantity has an E on the numerator, we can write it as 1.60206 into 10 raised to minus 19 coulombs divided by M gives 1.75875 into 10 raised to 11 coulombs per kg. From here on out, it's just a simple case of substitution. So what we can do is we can write mass as 1.60206 into 10 raised to minus 19 coulombs divided by the charge to mass ratio, which is 1.75875 into 10 raised to 11 coulombs per kg. So now we need to do the division of these two in order to get our answer. Using approximation, we can shorten 1.60206 into 1.6. So it'll be 1.6 into 10 raised to minus 19 coulomb. And the way we did it is that since 6 is greater than 5, 0 becomes 1. 1 is less than 5, so 2 remains the same. 2 is less than 5, so 0 remains the same. 0 is less than 5, so 6 remains the same. So 1.6 into 10 raised to minus 19 divided by 1.75875. How do we use estimation here? So we have an odd number here, and so if 5 comes, then 7 becomes 8, and 8 is greater than 5, so this 8 becomes 9. 9 is greater than 5, so this 5 becomes a 4. But since 4 is less than 5, this 7 becomes a 7. So what we'll get is 1.7 into 10 raised to 11 coulombs per kg. And so when we do the division, we'll get the answer in kg. Now, we have 10 raised to minus 19 divided by 10 raised to 11. So we can write 1 by 10 raised to 11 as 10 raised to minus 11. And so 10 raised to minus 19 into 10 raised to minus 11 will be the same as 10 raised to minus 19 minus 11, which is 10 raised to minus 31. So now we got our power. All that remains to be done is a simple division of 1.6 by 1.7, which we can make it as 16 by 17 when dividing for our convenience. So since 17 does not go into 16, it becomes 0. Point, we add, and then 9. So we get 153. And then we get a 70. And then it's a, so we got something 0.9. So the right answer would be the one with 9 in its answer. So the only quantity here which has the number 9 in the part before the decimal, that is the ones place, is option B, 9.1091 into 10 raised to minus 31 kg. And so on approximation, we're getting option B, 9.1091 into 10 raised to minus 31 as our answer. So option B is the right option. So we found the mass using the charge to mass ratio found by Thomson and the charge of the electrons given. So we approximated it, and then it's a simple matter of substitution. So it is 9.1 into 10 raised to minus 31 kg. Let's move on to our next question. The energy of an electron in the first energy level is given as minus 21.79 into 10 raised to minus 12 erg per atom. Erg is another unit. It's the CGS unit of energy. And we're asked to find out the energy of the electron in the second energy level. So how do we solve this question? This question looks difficult, but it's really easy. So let's find out the formula for the energy of an electron in the nth energy level. So that will be equal to 13.6 z square by n square. 13.6 is a constant. Z square is the atomic number. Z is the atomic number, and n is the energy level, which basically refers to which shell of the electron. So we know that the energy of electron in an nth energy shell is 13.6 z square by n square. From here, we can work out a relation that En is proportional to 1 by n square. since it's present in the denominator, so the energy of the electron will be inversely proportional to the square of the energy level that the electron is in. So using this idea, we can substitute E is equal to 1 and E is equal to 2. So E1 divided by E2 for any one element. We can write the energy of the electron in its first shell divided by the energy of electron in its second shell as 1 by the first shell whole square divided by 1 by second shell whole square. So 1 by 1 square divided by 1 by 2 square would be similar to 1 by 1 square into 2 square. So basically we're getting 2 square by 1 square as the ratio of E1 by E2. So on getting the squares, we can write E1 by E2 as 4 by 1. So now we have the value of E1 as minus 21.79 into 10 raised to minus 12 ergs given. So we can just substitute that value over here in this equation. So it's minus 21.79 into 10 raised to minus 12 divided by E2 is equal to 4 by 1. So on cross multiplication for E2 is equal to minus 21.79 into 10 raised to minus 12 multiplied by 1. So that's still the same. So over here, we'll get E2, the energy of the electron in the second energy level, as minus 21.79 into 10 raised to minus 12 divided by 4. So now basically, we have to do the division of minus 21.79 by 4. So E2 is basically minus 21.79 divided by 4 into 10 raised to minus 12 erg per atmosphere. That is the unit. So now it's really simple. We'll just divide 2179 by 4 and then use the appropriate decimal placement. So 4 goes into 21 5 times. So 21 minus 20 is equal to 1. 4 goes into 17 4 times. So 16, so that's 1. 4 goes into 19 4 times. So 19 minus 16, that is 3. And now in order to go any further, we'll have to put a decimal point here. So a 0 comes there. So 4 goes into 37 times. So 30 minus 28, which is 2. And again, if we do the division, so we'll get 544.75 as the quotient with 0 remainder. So we have 544.75. But that is when the quantity is 2179. Over here, the quantity is 21.79. So basically, you have to pull this decimal point 2 steps to the left, right here. And so our answer for 21.79 divided by 4 is 5.4475. And since there's a minus, that does not get eliminated, so it stays there. So E2 will be minus 5.4475 into 10 raised to minus 12 erg per atmosphere. So when we look at our options, we find that option B is the closest to our answer. So option B is minus 5.447 into 10 raised to minus 12 erg per atmosphere. And what we got is minus 5.4475 into 10 raised to minus 12 erg per atmosphere. So now we can safely say that option B is the right answer to this question. So the energy of electron in the second energy level in the given situation is minus 5.447 into 10 raised to minus 12 erg per atmosphere. Now let's move on to the next question. A deuterium nucleus contains 1 proton, 1 electron, 1 proton, 1 neutron, 2 protons, 1 electron, and 1 proton, 2 electrons. So what is deuterium? Deuterium is an isotope of hydrogen. So what that means is that deuterium has the same atomic number but different mass number. Z is for atomic number, A is for mass number. So both of them have the atomic number 1 because the atomic number for hydrogen is 1. So deuterium also has 1 proton in its nucleus, but there is a different mass number. Why is that? This happens because the isotope has more number of neutrons. So for deuterium to be different from hydrogen, it should have 1 neutron in its nucleus in addition to 1 proton to give a different mass number. So having said that, let's look at our options. Options A, C, and D are incorrect. The reason being that they say that an electron is present in the nucleus, but electrons are always present in the shells around the nucleus. So they orbit in energy levels around the nucleus. So therefore option A, option C, and option D are incorrect. The right answer is option B, 1 proton, 1 neutron. Different mass number, but the same atomic number. And since the atomic number of hydrogen is 1, deuterium must also have 1 proton in its nucleus in order to get the same atomic number. So option B is the right answer. Now our next question. The outermost configuration of most electronegative element is Ns2Np5, Ns2Np6, Ns2Np4, and Ns2Np3. So how do we go about this question? So each subshell, S, P, D, and F, contain a different number of orbitals. S has 1, P has 3, D has 5, 3, 4, 5, and F has 7. 1, 2, 3, 4, 5, 6, 7. So the goal of every atom or element is to fill these orbitals, and each orbital can have 2 electrons. So an S has a maximum of 2 electrons, a P can have a maximum of 6 electrons, a D can have a maximum of 10 electrons, and an F can have a maximum of 14 electrons. So now we need to figure out which of these configurations is most electronegative. So what is electronegativity? This is the tendency to gain electrons. So the atom or element or ion has an incomplete electronic configuration, and in order to complete it, it needs to gain electrons. So suppose you need 5 sweets and you have 4, so you'll have the most urge of getting 1 more sweet in order to get 5. Than say if you have 3 sweets and you need to get 5, then there will be less electronegativity. So when we look at that, we know that the configuration given here is NS and NP. And the value of P differs, 5, 6, 4, and 3. And that number, the number on the exponent, would give you the number of electrons. And since each orbital can have 2 electrons, the maximum number of electrons in a p orbital is 6. So if a p orbital has 5 electrons, then it would have the most electronegativity because it only needs 1 more electron in order to get that stable electronic configuration. So therefore, we can find out that option A is the right answer. And if you want to make this even simpler, you can think of the most electronegative elements being halogens, such as chlorine, bromine, fluorine, iodine, etc. And they have the configuration NS2, NP5. Or if you're using the way that of finding it out using quantum numbers and orbitals and subshells, etc., then this is the way to go. A p shell needs 6 electrons, and the one which has 5 electrons would have the most electronegativity because it is the tendency to gain electrons. So it only needs 1 more, so it will have more electronegativity. So therefore, NS2 NP5 would be the right answer. So option A is the correct option. So the final option, the final question of today. Bohr's theory is not applicable to H, He plus, Li2 plus, and H plus. So Bohr's theory uses atomic spectra. So these are a way of measuring electrons using spectral lines. So it's kind of like the rainbow that we see, except that these are discontinuous. So therefore, they have this sort of spectrum in a box, which is used to find out the energy of the electrons. So for Bohr's theory to work, the given species must have electrons. So let's look at each of our options. A, hydrogen. Hydrogen is an atom with atomic number 1, so it should have 1 proton and 1 electron. So therefore, option A is incorrect because Bohr's theory is applicable because it has electrons. What about option B, He plus? So this is an ion, and the atomic number of helium is 2. So they have 2 protons, and since the charge on helium is plus, it means that there has been a loss of electrons. So there'll be only 1 electron orbiting the helium nucleus. So there is still 1 electron. So option B is also incorrect because it has an electron. And for lithium, it should be having 3 protons because the atomic number is 3, and 2 plus means there has been a loss of 2 electrons. So therefore, there is still 1 electron remaining. So option C is also incorrect because there is an electron in all 3 of these cases. However, in the 4th case, H plus, we said that hydrogen has only 1 proton. And for this nucleus to be neutral, it should have 1 electron. But the configuration given is H plus. So plus means 1 electron is lost. So now there are no electrons present here. So Bohr's theory of atomic spectra is not applicable to an H plus ion because the atomic spectra is used to measure the energy of electrons, and H plus has no electrons. So option D is the right option. So there are a lot of questions about the chapter structure of atoms, but due to time constraints, we won't be able to discuss everything. However, what we can do is give you the description of the other videos about structures of atoms in the description down below. So be sure to go there and click the description and check out our other videos on structure of atom and other chapters on chemistry. So we at Brain Blitz Audios are a free educational channel providing quality content to everyone. So to be a part of our channel, you can subscribe to our channel and hit the notifications button to receive more information and more episodes of Structure of Atom in NEET preparation or our other great content such as Learn Awards, Mind Maps, CBSE board exam prep, etc. So until the next episode, take care, stay safe, ta-ta for now.